Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A challenge of profound geometric elegance, bequeathed by the master of Syracuse, had lingered for over a millennium. In his treatise, On the Sphere and Cylinder, Archimedes posed a question of deceptive simplicity: to pass a plane through a sphere in such a way that the two resulting segments possess volumes in a predetermined ratio. For centuries, this problem remained a monument to the limits of classical geometry, a puzzle to be contemplated, admired, and ultimately left unsolved by the methods of ruler and compass alone. Its solution lay dormant, a whisper in the halls of Alexandria, awaiting a mind equipped with a different set of intellectual tools, a new language capable of describing relationships that pure form could only suggest. That mind would emerge in the vibrant heart of the 9th century Abbasid Caliphate, Baghdad. Here, in the crucible of the Beit al-Hikmah, the House of Wisdom, the intellectual inheritance of the ancient world was undergoing a spectacular transformation. Greek, Persian and Indian texts were being translated with a fervent, systematic energy, creating an unprecedented confluence of ideas. This was an environment of intellectual synthesis, where the geometric proofs of Euclid and the astronomical models of Ptolemy were placed in direct dialogue with the numerical systems of India and the algebraic innovations taking root in the very soil of Mesopotamia. Within this dynamic milieu worked the Persian scholar Abu Abdullah Muhammad ibn Isa Al-Mahani. He was a figure perfectly representative of his time and place, a polymath whose work would span the celestial and the abstract, the observed and the theoretical. Before Al-Mahani would confront the ancient ghost of Archimedes' sphere, he first established his reputation with his eyes turned toward the heavens. His primary vocation, and the source of his initial renown, was as an astronomer of extraordinary diligence. From approximately 853 to 866 of the Common Era, Al-Mahani undertook a series of meticulous astronomical observations from Baghdad. Surviving records, most notably those compiled by the later astronomer Ibn Yunus, attest to the precision and scope of this work. He documented a series of lunar and solar eclipses, providing timings and magnitudes that were invaluable. He also recorded the conjunctions of planets, those moments when Mercury, Venus and Mars appeared to align in the sky, celestial events that held deep astrological and calendrical significance for the Abbasid court. The central scientific problem of his astronomical era was one of refinement. The Ptolemaic system, a geocentric model of breathtaking mathematical sophistication, provided the dominant framework for understanding the cosmos. Its system of epicycles, difference and equants offered a powerful predictive engine for planetary positions. Yet, with the passage of centuries, small but persistent discrepancies between the model's predictions and actual observations had accumulated. For the functioning of a vast empire, this was a practical concern. The Islamic calendar is lunar, requiring accurate predictions of the new moon. The determination of the Qibla, the direction of prayer toward Mecca, was a problem of spherical trigonometry dependent on sound astronomical data. Furthermore, the practice of judicial astrology, a serious instrument of statecraft used to determine auspicious moments for political and military action, demanded the most accurate possible forecasts. Al-Mahani's great contribution to this enterprise was empirical. His work represents a deep commitment to the foundational and often unglamorous task of data collection. He was building a more robust empirical bedrock, where Ptolemy had worked with the observations available to him in 2nd century Alexandria. Al-Mahani was generating a fresh, high-precision dataset from a new geographical and temporal vantage point. His series of timed eclipses, and observed conjunctions provided his contemporaries and successors with the raw material needed to check, challenge, and ultimately improve the parameters of the Ptolemaic models. This was the slow, patient work of science, the accumulation of reliable facts upon which grander theoretical structures are built. His observations formed a vital resource for his colleagues at the House of Wisdom, including the famed Banu Musa brothers, who themselves were engaged in ambitious projects of measurement and mechanics. It is with this established reputation for scientific rigor that Al-Mahani eventually turned his formidable intellect back toward the earth, or rather toward the idealized forms of geometry. His mind, trained to find order and predictability in the complex dance of the planets, was uniquely prepared to see an old problem in a new light. The Archimedean challenge of the sphere was untouched by the observational tools of the astronomer, yet it presented a parallel search for precision and certainty. He perceived that the limitations of the Greek method, its reliance on what could be physically drawn, might be overcome by a different kind of abstraction. He envisioned a path forward by translating the spatial relationships of the sphere, its radius, the height of the cutting plane, the volume of the segments, into the symbolic language of algebra, a discipline that was then coming into its own as a powerful analytical science. This decision to reframe a classical geometric puzzle as an algebraic inquiry was a momentous step, marking a conceptual shift in the history of mathematics. He stood at the threshold of transforming a problem about physical space into a problem about the relationship between unknown quantities, ready to write the first chapter in a story that would captivate mathematicians for generations to come. The intellectual challenge posed by Archimedes to section a sphere according to a precise ratio now became the focal point of Al-Mahani's mathematical energies. He approached this puzzle with the mind of an astronomer, accustomed to wrestling with the complex motions of the heavens, yet he sought a solution within a purely terrestrial, abstract domain. The Greek tradition, magnificent in its geometric proofs, offered a toolkit of straightedge and compass. This was the language of constructible reality, of figures that could, in principle, be drawn. The Archimedean problem, however, whispered of a deeper complexity. Its solution was bound up with relationships that resisted simple geometric construction. The problem required a move from the visual and tactile world of lines and circles into a realm of pure symbolic logic. Al-Mahani's great insight was to recognize that the key lay in this very translation. He would take the physical parameters of the sphere and its segments and recast them as terms in an algebraic sentence, a form of inquiry whose power was only beginning to be fully appreciated in the intellectual centers of Baghdad. The problem itself, from Archimedes' work on the sphere and cylinder, is elegant in its statement: to cut a sphere with a plane, such that the volumes of the two resulting segments stand in a predetermined ratio to one another. Imagine a sphere of a known size. The task is to find the exact position of a flat slice that divides the whole volume into, for example, a smaller piece and a larger piece, where the larger is exactly twice the volume of the smaller. Archimedes had analyzed the problem and understood that it led to a cubic relationship, but he had left its algebraic formulation and solution for a future generation. It was this ancient, implicit challenge that Al-Mahani made explicit. His process was a masterpiece of analytical transformation. He began with the known geometric principles. Archimedes himself had established the formula for the volume of a spherical segment. Al-Mahani took these established truths as his axioms. Let us denote the radius of the sphere as arm and the height of the smaller spherical segment as the unknown quantity. The height of the second, larger segment is consequently the diameter minus x, or 2 times r minus x. The volume of each segment is a function of the sphere's radius and the segment's height. Al-Mahani set up a proportion. The volume of the first segment is to the volume of the second segment as the two numbers of the given ratio. Let us call them min and known. This proportion, expressed geometrically, is cumbersome. It involves multiple terms related to the radius and the unknown height. The true intellectual alchemy occurred when Al-Mahani began to manipulate this statement using the rules of algebra. He cross-multiplied, expanded terms and gathered like quantities. He was operating on the relationships themselves, detached from their physical representation. Through this systematic algebraic reduction, the clutter of the geometric description fell away, revealing a stark and beautiful underlying structure. The intricate spatial problem of volumes and ratios simplified into an equation of breathtaking clarity, an equation involving only the unknown height x, and constants derived from the sphere's known dimensions and the given ratio. The result of his derivation was the equation that would forever bear his name. In its normalized form, it is expressed as x cubed plus a equals b times x squared. Here, x is the unknown height of the plane cut he was seeking. The terms of b are constants, known numbers determined by the initial conditions of the problem, the size of the sphere and the specified ratio of the volumes. The term b was a composite of the sphere's diameter and the ratio representing a known volume, while the coefficient b was simply the sphere's diameter. The entire, complex, three-dimensional challenge of Archimedes was now encapsulated in this single line of algebraic script. The physical act of slicing a sphere was transformed into the abstract act of finding the root of a cubic polynomial. This was a profound conceptual leap. The solution was a number, and finding it required a new set of intellectual tools. The formulation of this equation was in itself a historic achievement. It represented a powerful demonstration of how algebra could serve as a universal language for describing quantitative relationships, transcending the limitations of constructive geometry. It established a clear bridge between the ancient geometric world of the Greeks and the burgeoning algebraic science of the Islamic Golden Age. Al-Mahani had taken a problem that was geometrically awkward and rendered it algebraically pristine. He had isolated the essential difficulty and given it a name and a form. Having forged the key, however, he found the lock would yield to no tool at his disposal. The mathematical world of the 9th century had powerful methods for solving linear and quadratic equations, thanks in large part to the systematizing work of Al-Khwarizmi. These methods were algorithmic and certain. A cubic equation, with its term of the third power, x cubed, presented a barrier of a completely different order. There was no general procedure, no established algorithm for finding the value of x that would satisfy the equation. Historical accounts, such as the 10th century catalogue of Ibn al-Nadim, the Fairist, record Al-Mahani's intense and prolonged struggle with his own creation. He had successfully climbed a formidable intellectual mountain only to find himself on a high plateau, staring at an even taller, unscalable peak. The solution remained elusive. This impasse, this celebrated failure, is perhaps the most important part of the story. His inability to solve the equation was anything but a personal shortcoming. It was a diagnostic moment for the entire discipline of mathematics. Al-Mahani's work established a clear, unambiguous benchmark for the limits of contemporary algebraic knowledge. The Mahani equations became a challenge problem that echoed through the halls of the House of Wisdom and beyond. It was a famous, unsolved puzzle that tantalized and frustrated the greatest minds of the era. Its very existence was a catalyst for innovation. By formulating the problem so elegantly, Al-Mahani had done more than ask a question. He had defined a new direction for research. He had created a mathematical Everest, and its presence on the horizon compelled future mathematicians to develop new techniques and new ways of thinking. The problem demanded a synthesis of disciplines, eventually leading his successors to explore the intersection of conic sections, parabolas, hyperbolas and ellipses as a geometric means to find the roots of these stubborn cubic equations. His struggle illuminated the path forward by revealing the precise location of the frontier. While this grand challenge occupied one part of his formidable intellect, his scholarly mind was simultaneously probing the very foundations of the mathematical language he was employing, questioning the axioms and definitions that underpinned the entire edifice of geometry. His deep engagement with the algebraic frontier ran parallel to a profound interrogation of the geometric bedrock upon which all his work rested. This dual intellectual motion, one pushing forward into new territory and the other digging down to test the very axioms of the old, defines the full scope of Al-Mahani's contribution. His mind, having sculpted a novel problem from the heart of Archimedean geometry, turned with equal intensity to the foundational texts of Greek thought, engaging with them as a critical partner in a continuing dialogue. He treated the works of Euclid, Archimedes and Menelaus as living documents, sources of immense wisdom that also contained ambiguities and conceptual hurdles, demanding fresh interpretation and occasionally radical reformulation. The most telling example of this critical engagement lies in his commentary on Euclid's Elements, specifically its fifth book. Book 5 stands as one of the supreme achievements of Greek mathematics, a towering intellectual edifice containing Eudoxus of Kinetus's theory of proportion. This theory was a masterful response to the crisis precipitated by the discovery of incommensurable magnitudes, lengths like the side and diagonal of a square, whose ratio could be expressed by no pair of whole numbers. Eudoxus's solution was one of exquisite, almost ethereal, abstraction. It circumvented the need to assign a numerical value to a ratio. Instead, it provided a powerful criterion for determining when two ratios are equal. The definition states that the ratio of a magnitude A to a magnitude B is the same as the ratio of C to D. If for any whole numbers m and n, whenever m times A exceeds n times B, then m times C also exceeds n times D, and similarly for the cases of equality and being less than. This was a definition of impeccable logical integrity. It worked flawlessly for both commensurable and incommensurable quantities, sealing the logical fissure that had threatened to undermine Greek geometry. For the purpose of rigorous proof within a purely geometric system, it was perfect. Yet for the mathematicians of 9th century Baghdad, who were forging a new and powerful algebra, the Eudoxian definition presented a peculiar kind of obstacle. It was a relational comparative tool. It told you everything about the equality of two ratios, while remaining completely silent about the intrinsic identity of a single ratio. One could use it to prove that the ratio of a circle's circumference to its diameter was a constant, but the definition offered little help in computing that constant. It was a language of pure logic, detached from the operational, computational spirit of algebra. Here Al-Mahani perceived a fundamental disconnect. He saw a need for a definition of ratio that was constructive and algorithmic, one that could be expressed in the language of number and process. In his commentary on Book 5, he advanced a bold and ingenious alternative. He proposed to define the ratio of two magnitudes by recourse to the procedure we now call the Euclidean algorithm, a method for finding the greatest common divisor of two numbers. Al-Mahani generalized this process to any two magnitudes, A and B. One would first determine how many times the smaller magnitude, B, could be subtracted from the larger, until a remainder smaller than B was left. This number of subtractions gives the first term of the ratio's representation. The process is then repeated with the remainder and the smaller magnitude b. To be precise, his method generates what we today recognize as a continued fraction. To find the ratio of a to b, one finds a sequence of integers, let's call them q sub 0, q sub 1, q sub 2, and so on. The first integer, q sub 0, is the whole number of times b fits into a. The next integer, q sub 1, is the number of times the first remainder fits into b. The third, q sub 2, is the number of times the second remainder fits into the first, and so forth. This sequence of integers, for Al-Mahani, was the ratio. For a rational ratio, the process would terminate, yielding a finite sequence. For an irrational ratio, it would continue indefinitely, generating an infinite sequence of integers that uniquely defined the relationship between the two original magnitudes. This was a revolutionary proposal. It sought to arithmetize one of the core concepts of geometry. It replaced a static, logical comparison with a dynamic, iterative procedure. The ratio was transformed from an abstract relation into a concrete, if potentially infinite, recipe of numbers. This approach had profound conceptual advantages. It provided a direct pathway to calculating rational approximations of irrational ratios, as truncating the continued fraction at any point yields the best possible rational estimate for a given denominator size. Al-Mahani's idea was a powerful move toward unifying the discrete world of arithmetic with the continuous world of geometry under the banner of algebraic process. It prefigured by centuries the development of real number theory, where infinite processes are used to define individual numbers. While his continued fraction definition of ratio was a work of brilliance, it was perhaps too far ahead of its time. The formidable authority of Euclid and the logical perfection of the Eudoxian definition ensured that the classical approach remained the standard for centuries. Al-Mahani's proposal became a fascinating but ultimately subordinate path in the history of mathematics. Yet, its existence tells us a great deal about its author. It reveals a mathematician with the confidence to challenge the very foundations laid down by the venerated Greeks, and with the vision to seek a more unified and computationally effective mathematics. This deep analytical spirit extended to his other commentaries. His work on Archimedes on the sphere and cylinder was the very source from which he extracted his famous cubic problem. This implies a level of engagement with Archimedes' text that went far beyond simple translation or preservation. He was grappling with the method of exhaustion, Archimedes' precursor to integral calculus, and interrogating the limits of the geometric tools available. Similarly, his commentary on Menelaus of Alexandria's Spherix was of immense practical and theoretical importance. Menelaus's work was the foundation of spherical trigonometry, the mathematics required to describe the positions and motions of celestial bodies. For a scholar working in Baghdad, a global center for astronomy, a meticulous commentary on Spherix was a vital contribution, refining the mathematical tools necessary for the observational programs of his colleagues. Through these scholarly activities, Al-Mahani functioned as a crucial intellectual conduit, a synthesizer who absorbed the corpus of Hellenistic mathematics and actively reshaped it. His commentaries were acts of critical appropriation, endeavors to make ancient knowledge more coherent, more powerful, and more aligned with the burgeoning algebraic worldview of his time. This deep engagement with the classical legacy, both in posing new problems and in re-examining old definitions, established a rich intellectual inheritance. The resolution of the challenges he posed and the full flowering of the algebraic geometry he helped to pioneer would fall to a subsequent generation of thinkers who stood upon the foundations he had so carefully interrogated. The most profound element of that intellectual inheritance, The very problem that had stymied its author awaited its resolution for nearly a century. The cubic equation derived from Archimedes' sphere and cylinder challenge, expressed as x cubed plus c squared b equals c sec squared, became a celebrated open question in the Islamic mathematical world. It stood as a monument to the limits of the current algebraic toolkit, a puzzle that could be elegantly stated, but whose solution remained elusive through purely numerical or simple geometric means. Its eventual conquest would require a thinker of extraordinary vision, one capable of completing the synthesis Al-Mahani himself had initiated. That thinker was Abu Ja'far al-Qasim, a 10th-century astronomer and mathematician from Khorasan. Confronting Al-Mahani's equation, Al-Qasim perceived that the path forward lay in a deeper fusion of algebraic statement and geometric intuition. His masterstroke was to translate the algebraic impasse back into the visual, spatial language of Hellenistic geometry, yet with a power and generality that the Greeks themselves had pursued differently. He recognized that the solution, the unknown value of x, could be materialized as a physical point in space, the precise location where two distinct conic sections intersected. This was a moment of profound intellectual synthesis. Al-Qasim demonstrated that Al-Mahani's equation could be solved by plotting two curves defined by Apollonius of Perga centuries earlier and finding their meeting point. He constructed a parabola and a rectangular hyperbola, each defined by an equation derived from the original cubic. The x-coordinate of their intersection point provided the positive real root that Archimedes had sought and Al-Mahani had formulated algebraically. The abstract algebraic variable became a tangible geometric length. This method was powerful, elegant, and generalizable. It provided a pathway for solving a whole class of cubic equations that were irreducible by simpler methods. Al-Qasim's success was a direct consequence of Al-Mahani's ambitious failure. The question Al-Mahani posed was so well formulated, so central to the integration of two mathematical traditions, that it compelled the creation of a new, more powerful methodology. His inability to find a solution became the very engine of progress, creating an intellectual vacuum that drew in the genius of his successors and demanded innovation. This resolution illuminates the core of Al-Mahani's historical significance. His legacy is defined by his role as a brilliant architect of mathematical problems. He was a pivotal figure in the transformation of algebra itself. Before him, in the work of predecessors like Al-Khwarizmi, algebra was largely a powerful set of computational algorithms, a practical science for resolving issues of inheritance, commerce, and measurement. Al-Mahani, through his deep immersion in the abstract world of Greek geometry, began to envision algebra as something more, a universal language for theoretical inquiry. He saw that its symbolic notation could be used to restate, generalize, and interrogate the most profound spatial questions posed by Euclid and Archimedes. His work on the Archimedean problem is the supreme example of this vision. He took a geometric challenge, one of ratios and volumes, and recast it into a purely algebraic form, an equation of powers and coefficients. In doing so, he demonstrated that algebra was capable of expressing relationships that were immensely difficult to handle within the framework of classical Greek geometric proof alone. He elevated algebra from a tool of calculation to an instrument of analysis, a system capable of representing abstract mathematical structures. This conceptual leap helped set the course for centuries of mathematical development, culminating in the work of figures like Omar Khayyam, who would later provide a complete classification of cubic equations and their geometric solutions, and eventually leading to the purely algebraic solutions of the Italian Renaissance. Al-Mahani's contribution was the critical act of posing the question in the right language, thereby revealing both the power of the new algebraic approach and its temporary limitations. His commentaries on Euclid and Menelaus served a similar function. They were exercises in clarification and critique, aimed at making the Hellenistic inheritance more rigorous and accessible for a new generation of scholars thinking in a new mathematical paradigm. He was building a bridge between two worlds, ensuring that the geometric wisdom of the past could flow into the algebraic framework of the future. His intellectual legacy, therefore, is one of catalysis and transformation. He was an essential link in the great chain of mathematical thought, a scholar whose own unresolved problems proved to be more fertile and more consequential than the complete solutions of many others. He mapped a new territory of inquiry, and even if he was unable to conquer it all himself, he provided the charts that would guide future explorers to its riches. In the grand narrative of scientific progress, certain figures are remembered for their definitive answers, for closing a chapter of inquiry with a triumphant solution. Others, perhaps more subtly influential, are defined by the sheer quality of their questions. Abu Abdallah Muhammad, ibn Isa Al-Mahani, belongs firmly in this second vital category. He stands as an archetype of the catalytic thinker, the scholar whose work creates the productive friction from which new ideas spark into existence. His engagement with the classical heritage was deep, critical, and transformative, pushing the boundaries of what algebra, as a discipline, was thought to be capable of. The ultimate resolution of his famous cubic equation by Al-Khazin, using the sophisticated geometric machinery of conic sections, is the perfect epilogue to his career. It demonstrates that the problem he posed was precisely the right one, a challenge perfectly calibrated to force a synthesis between the geometric past and the algebraic future. The vitality of a field of knowledge is measured as much by the richness and difficulty of its open problems as by its settled theorems. A discipline without profound unanswered questions is a discipline in danger of stagnation. Al-Mahani's career is a powerful reminder of this truth. He bequeathed to his successors a magnificent, unanswered question, one whose resonance would shape the course of mathematics for a century. His work stands as an enduring testament that the most valuable inheritance a thinker can offer is an intellectual challenge that demands and cultivates the genius of generations yet to come.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.